A pressurized water reactor power plant comprises a nuclear island with buildings that house specific equipment: the reactor, nuclear auxiliaries, safeguard systems, fuel, and diesel generators. The plant also includes a conventional island with a turbo generator set which produces electricity. The energy production process begins with the fission of uranium atoms inside the reactor core, which contains nuclear fuel assemblies. Each of these assemblies contains several hundred sealed tubes, each containing pellets of enriched uranium. Enriched because it contains a high proportion of uranium-235, the fissile element. In the process of fission, the collision between a neutron and the nucleus of a uranium-235 atom splits the nucleus into two fragments, ejecting 2 or 3 neutrons. These neutrons are free to split other fissile nuclei, thus maintaining a chain reaction which produces high levels of heat within the fuel tubes. These tubes then transfer heat to the primary circuit water, simply by contact. The chain reaction is controlled at all times. Control rods made from neutron-absorbing material are lowered into or withdrawn from the core to control the nuclear reaction. In the event of an emergency, the control rods drop by gravity into the core, stopping the chain reaction within 2 seconds. The primary circuit is a closed circuit of pressurized water whose function is to extract heat from the nuclear reactor. This water enters the reactor vessel at 296 degrees Celsius, is heated by contact with the fuel assemblies, and exits at 327 degrees. The water then passes into a steam generator, where it transfers its heat to a secondary water circuit. Water in the primary circuit is pumped through the various components. To assure that water in the primary circuit remains in a liquid state, a pressurizer maintains the constant level of 155 bars. Hence the name, pressurized water reactor. The reactor shown here has 4 primary loops surrounding the reactor vessel. One of the fundamental features of reactor safety is the interposition of 3 successive sealed barriers between the radioactive products and the environment. The fuel assembly tubes, the metal containment of the primary circuit, the concrete containment building. Within the steam generator, heat stored in the primary circuit water is transferred to a secondary circuit. The heat exchange occurs within a bundle of around 6,000 inverted U-shaped tubes. The heated water enters the bottom of the steam generator, transfers its heat to the secondary system water through the U-tubes, then returns to the reactor vessel for a new cycle. Water in the secondary circuit flowing around the wrapper of the U-tube bundle is heated to boiling temperature, turns into steam, and then travels to the turbine set in an adjacent building. After passing through the turbine, the steam is recondensed into liquid water and returned to the steam generator for another cycle. Steam pressure from the secondary circuit drives the turbo generators to produce electricity. Secondary circuit water is cooled by a third circuit, which can be sea or river water. The condenser uses water pumped from outside the power station to cool the secondary circuit. To summarize, a nuclear power station is essentially 3 circuits: the primary and secondary circuits, which are both closed, and the cooling circuit, which opens to the exterior. All three work together to transform the energy liberated by nuclear fission into electricity. Harnessing the proven and optimized technology of pressurized water reactors enables us to meet the energy needs of society in a most efficient and safe manner.